All right, recording's ready, rolling. So we've been outside, we came back. You guys were keeping this data table, different trials. It would have been, of course, a consistent height. It was probably about a consistent horizontal displacement too. Yeah, there's no real independent variable with this one. Right? Maybe you just do a few launches just to reduce experimental error. Right? Right, you guys been doing this AP style write-up that I got started for you. And I think some of you guys getting about to a conclusion. So walk you guys through the solution. Right, that's what the setup looks like. Right, here is what I walked you guys through yesterday, which really is the solution to your lab. Right? So the height of the ledge will determine the time of fall. Oh, that's through that first kinematic equation. That's this one here, right? Now, guys, why? Wait a minute. Doesn't this apply V naught is 0? If you use a simplified version and say V naught 0, is that true? Is V naught 0 right there? Guys, this is V naught 0 in what direction? In the vertical direction. Guys, when that ball is leaving the launcher, what is its vertical velocity equal to just at the moment it's leaving? 0. That's why this goes to 0. Because vertically, this is actually V naught in the y direction. Maybe add to that subscript, right? That's why this turns into this, right? Now you can rearrange this to solve for the time of fall. Guys, would this time of fall be identical to if you just dropped the ball? Just dropped it? Yeah, it'd be identical, right? Right. Good. So V naught 0 in the y direction. Now the ball's moving really fast as it leaves the launcher, but that's all in the x direction. That's like V blast. You can call it V sub x. Right? Now, however much time it takes to get from here to here is the same whether you analyze it vertically or horizontally. Therefore, you can take this expression for time, pop it right there. Okay. Okay. So then, see the horizontal displacement divided by that expression for time. Flip and multiply the whole deal. All right. Here's the general solution to your lab. AP would expect you to be able to derive this just from variables exactly like it is on this page. Right? This is like an AP level question. Okay. Right, so you guys good so far? Right. So there's kind of the answer just in terms of variables. Right. We guys asked you guys some specific numbers. What'd you guys get for the height of the balcony? Okay, I'm hearing a little over 5 meters. What else do you guys get? 384 centimeters. Okay, so I'm hearing a little over 5 meters, a little less than 4 meters. What else do you guys get? Oh, okay. Yeah, so I guess if it depends if did you have to launch like on the floor, did you put it above like on top of the railing? Because that would add about a meter, right? Yeah. Okay. So you might actually have different heights depending on whether you perch this on top of the railing or you put it like right at the base on the floor, right? Yeah, I think you should get somewhere in there, somewhere about 4 meters, 5 meters, somewhere there, about 4 or 5 meters. Okay. Which corresponds to maybe almost a second of fall time, almost a second, right? But in the general solution, the time gets substituted out anyway. Okay. Guys, what were some horizontal displacements you guys got? How far did you guys get?
The distance?
Yeah.
Just about 6 meters. About 6
meters, right? Okay, so let's see. If it went 6 meters across and it fell in approximately a second, I'm rounding a little bit, right? Because about a second to fall 5 meters. Right? Right. What would the blast speed be approximately? 6 meters per second. Boom, done. Right? Now, so for your guys' results, did you guys get V blast is somewhere in that ballpark, right? Maybe 5, 6, 7 meters per second, somewhere in there. Right? Would have been. All right, you guys ready to see the AP style solution? Square yourselves. All right, I've got these points add up to 12. So projectile labs. Right. Well, this is here. The one on the right is what's the optimal firing angle for this displacement. So right, here's firing speed of the launcher. Right. Zoom in here. Right, so there's the question: what's the firing speed of the launcher? Right. Measuring tools: 1 point for a meter stick or trundle wheel or both. Right. And 1 point for a scale, which I said to also have the scale, right? So just so you can record the mass of the ball, because that might make a difference too, right? You may mention these other tools, but you don't really need. Actually, I discourage you from using stopwatch. So you probably didn't. You definitely have something to measure displacement, right? Meter stick, trundle wheel. Okay. Right. So there, boom, boom. There's 2 points. You guys got the first 2 points, right? Data gathering procedure. Set up the ball launcher top of a cliff edge. Aim it horizontally. Boom. I gave that one to you, right? So 1 point for a brief description of the setup. Everybody's got that because I gave it to you. I wrote that right here. use the scale to measure the mass of the ball. Oh, well, you have that too because I also gave that to you. I said, you're good, right? That's gonna be controlled. 1 point describing control. Right. Measure the height of the cliff with the meter stick. Right. 1 point for use of the meter stick to measure the height. Step 4, launch the ball and spot where it lands. Measure this horizontal displacement also with the meter stick or the trundle wheel. You can set the trundle wheel. Right. 1 point for use of the meter stick or the trundle wheel. Right. There's another point right there. Bam. Okay. Repeat that process several more times and find the average displacement. Right. So 1 point for multiple trials. Maybe I should have added on to that. I should have said to reduce experimental error or reduce random error, right? Because that would be the purpose of doing that, and that's what AP grader would be looking for, right? But they would be looking for multiple trials for sure, right? That's always a point. That's always a point. Multiple trials. Okay. Right, you guys doing good so far? Okay, good so far. All right. Hopefully you guys are getting all these points. Okay. Now analysis time. Right now I have 3 different analyses depending on the setup. Right? I had you guys all streamlined into doing one of these, but let's look at all of them real fast. Right? Launch the ball horizontally from the top of the cliff. That's exactly what I had you guys do. You could have launched the ball. You could have put the cannon on the ground and launched at some angle and spotted where it landed. Maybe use like a range formula type thing. Right? Now that would have been a lot more mathematically involved because you could have done that. Also, you could have determined the launch speed by launching it straight upward. See, like, what is its maximum height? Right? Could have done that too. That also, there would have been a way to determine the launch speed. Like, if I've lost it straight up, how high does it go? Okay, no, but streamline here. I'm having everybody just do this one. Okay? So, rearrange h equals 1/2 gt squared to determine the fall time. Right? Time is the square root of 2h on g. Right? And then after that, determine the horizontal velocity, right? I'll call it v blast, same thing because you aimed it straight horizontal, by doing how far across divided by how much time, and time is this funny expression right here in terms of the height and the gravity. Right? So let's call that 2 points for correct use of kinematic equations and 2 points to rearrange it to get solve for v blast. Right? I'm trying to make the points add up to 12 because this would be like a 12-point FRQ. Okay, that's exactly how they would do that, but some version of that. 12, so 2 points for pulling out kinematic equations. H equals 1/2 gt squared. X equals v sub x times t. Right? And then the second point for rearranging those, substituting, and getting some version of that, just like I showed you guys in the here. Okay. If you came up with this, then even better, right? Because there's a general solution to the whole lab. Okay. You guys good so far? Okay. Finally, conclusion. The blast speed of the launcher is blank meters per second. Of course, you have a number there, right? What's the number you got? Who got a number for how many meters per second? What do you guys get? Yeah, what did you get?
I got 10.55 per hour.
10.55? Right. That sounds like a reasonable number. Okay. Now there's a lot of precision. I might call it like 10.6 or something, but AP is not a stickler about sig figs, so they would take 10.55 meters per second. Right? You guys do have units attached to that number, right? Nobody wrote the velocity is equal to 9. Nobody wrote that, right? You said like 9 meters per second, right? Of course you did. Of course you did, because you guys know numbers have units attached to them. Okay. All right. So you guys got yourselves scored out 12. Again, hopefully you picked up almost all those points, maybe all those points. If you're a few points short, it's not going to knock your class grade, but as long as you did all that, right? So you collected the data, you have the 5-part write-up, go ahead and score yourself out of 12. All right, you guys good? All right, now hang tight because we do have some class time. If you want to go over, here, make the most use of our time here. You guys remember these chapter 3 puzzles? Right? Now, all the ones that I circled 7 problems, right? 7 puzzles. They're all projectiles except for this one with they've got listed as a mule. That's hard to pronounce. I'm just going to call it a donkey. Right? You guys see the donkey right here? Right. Now, this is the only non-projectile. It is 2 dimensions. This is actually a bridge to the next section we're going to do that involves forces. Right. So I want to walk you guys through this because I think you guys should be able to figure this out by the weekend. But it takes a little bit thinking. So here's the deal. We got helicopter view. Shows 2 people pulling a stubborn donkey. 2 people pulling a stubborn donkey. You guys see like an XY set of axes, and they're both trying to pull it maybe like in the Y direction, which would be forward. One guy's pulling forward to the left. One guy's pulling forward to the right. You guys see that? Right. But from the donkey's point of view, do you think that there's effectively one net force, right? Right? Because they can pull it all different directions, all at different magnitudes, but there's only one net effect, isn't there? Right? Okay. So what is the net force that this donkey would feel? Right? And then okay, and there's some follow-up questions. Like, suppose the donkey is not moving at all. Well, there's probably a friction force where, what's the friction force equal to? So that would zero out the total force. Okay. Right, so I really want to focus though on what is the net force on that donkey. So here's how we do that. Okay. Of course, you guys have the solutions available on Google Classroom and also on your desk right now. Okay. But those solutions, actually, I just did the algebra type work on it. Okay. I definitely want to do a picture with you guys, draw a picture. Okay. So I got an XY set of axes going on. Got my x-axis and my y-axis. Okay. Let's call y the forward direction. Right. We're trying to pull this donkey forward. Here's my donkey, floppy donkey ears, donkey tail. Oh yeah, donkey time. Now I'm going to make up some numbers that are different from the book. Just give you guys some different work with. Okay. Let's say one guy is pulling with, I'll call it the force on the left side is equal to, let's go 500 newtons. And let's call this angle, 37 degrees, 37 degrees. Ooh, I sure do like that number. And let's say another guy's pulling with, let's say force on the right is equal to 400 newtons. 400 newtons. Okay. Newtons is the measure of force. Okay. And let's call this angle here, how about 41 degrees, just something crazy, right? Okay, you guess that? Okay. Now, do you guys think that the donkey is overall being pulled forward-ish? Definitely forward-ish, right? Is it more to the left-ish or more to the right-ish? Well, that's a little bit harder to tell. And actually, I don't even know. I just made up those numbers, so I don't know that. Okay. But we're about to find out, right? Now, the way we're going to approach this is we're going to break each of these vectors into components. That's the first step of so many problems, including projectile problems, right? Right? Like if you have a cannon on the ground, you ramp out some angle, blast it out. Remember, the very first step is break that velocity into components. Okay? We're going to do the same thing with force vectors. So this guy pulling forward to the left, how much forward and how much to the left? And the guy pulling forward to the right, how much forward and how much to the right? Right? You guys get that? See how I'm breaking these into components? Okay. Now I'm doing horizontal and then vertical, tip to tail. Okay. But you could do forward and then horizontal, right? You could go up and left and up and right, but I'm doing left up and then right up, right? Is that? Look at there, look at there. Right, you guys see all that so far? You guys good? Right. How much forward? How much to the left? How much forward? How much to the right? Right, right? You guys see that? Okay. Right. Now, guys, what is this angle right here? What's that angle? 37 degrees. What is this angle right here? 41 degrees. Okay. Hey, can you guys apply sine and cosine to figure out what are these components? You guys do that? Is that? Here. See if you can stay a step ahead of me. Step ahead of me. So this one, maybe I want to do 500 newtons multiplied by cosine of 37 degrees. This leg right here, I'll call 500 newtons times sine of 37 degrees, because that leg's opposite of the 37-degree angle. Okay. This one right here, I'll call 400 newtons times cosine of 41 degrees. And this one right here, I'll call 400 newtons times sine of 41 degrees. Right? You guys see that? You guys see that? All right. Let's get some numbers. 500 cosine 37 degrees. Ooh, this is like, well, here, I'll go ahead and keep it. 399 newtons. How about that? 399 newtons. If you want to say 400 newtons, that's kind of what I was trying to get at. That might be okay too. Okay. How about, what if I flip in a sine right here? Hey. 301 newtons. 301 newtons. Right? This is all middle set. This is you guys see this is going to be another process question. Projectiles are process questions. This is a process question. There's lots of middle steps. Okay. Okay. How about these components over here? What is 400 cosine 41 degrees? That is 302 newtons. What is 400 times sine of 41 degrees? That's 262 newtons. Okay. There's also some extra decimals. I'm just gonna round to the nearest whole number. Just get the idea here. Okay. All right. Right. You guys see this burgundy color? I got 4 components, and I kind of circle those with a dash outline. You guys see those? You guys see those? Right. Right. So yeah, the donkey's definitely being pulled forward. They're both pulling forward. But in terms of horizontal, it's a fight. One guy says left, one guy says right. Guys, who wins? The guy pulling left or the guy pulling right? The guy pulling left. Ah, it's a greater force. Okay. Now, you guys ready to find some net forces? Net forces? Yeah. Oh. So the sum of forces in the y direction, you guys know sigma means the sum of, right? You could also call it the net force, is 399 newtons forward plus 302 newtons forward. What is that? 4, 5, 6, 701, I think. Is that 701 newtons forward? I think that's what that is, right? Right, true? Right. And what is the sum of forces in the x direction? Well, that'd be, ooh, maybe I have to throw a negative sign on one of these, right? I think it sounds kind of like that. Okay. So let's go 301 newtons to the left minus 262 newtons to the right. Do something like that. I should mental math that. 39 newtons, that looks about right. 39 newtons to the left overall. Yeah. Right? You guys see that? 39 newtons to the left. Right? Right. Finally, let's put this all together. So we're going to go back to the donkey. Donkey ears, donkey tail. He's being pulled overall 701 newtons forward. He's being pulled overall only 39 newtons to the left. What 39 newtons to the left? Okay. That's going to create this here resultant. This here resultant. Can you guys do Pythagorean theorem? Pythagorean theorem? Here, I'll just go ahead and do this on the screen because we're running out of time. 701 squared plus 39 squared, square root of that. This ends up being 702 newtons. Okay. And finally, we need the direction. I'll call this theta. Guys, how do you get theta? Inverse tan, opposite over adjacent. Inverse tan, opposite over adjacent. I'm looking at 3.2 degrees, I'll say left of forward. So there you go. He's been pulled with the vector with a magnitude of 702 newtons and a direction of 3.2 degrees left of forward. All right, turn your lab into the great tray. Lab in the great tray. And you guys have a great rest of your day. Have AP Classroom done by tomorrow. Oh, yeah.